This is the first lecture for Unit 3, Module 1, Part A, introducing the ideas of kinetics, reaction rates, and rate laws. Kinetics is about the idea of, or concerns itself with, how fast a reaction is going. In other words, how fast are products getting made or reactants getting used up. Now you will hear that this depends, or read that this depends on the nature of reactants, which is fundamentally, fundamental, the ability of molecules to meet, and then the ability of molecules to meet. Molecules can't meet unless they're in contact with each other, naturally. The typical situation we will consider is mixtures of reactants, and the ability of molecules to meet will depend on the concentrations of reactants in that mixture. We will look at the effect of temperature. Reactions generally go faster as temperature increases. We will look at why that is and understand it as we get through the chapter. We will also touch on the subject of catalysis. A catalyst is a substance which can be introduced to a reaction. It's not consumed by the reactant. It's not a reactant or a product, but it makes the reaction go faster. We need, in this unit, to define what the rate is. Right. Let's do this by example. Consider this reaction, the combustion of butane. 2 butanes react with 9 O2 molecules to make 8 carbon dioxides and 10 water. For all of the species in this reaction are gases. Alright, so carbon dioxide and water are getting made. Butane, C4H10, and oxygen are getting used up. Here's how we can define a rate, R. Consider the change in carbon dioxide concentration with respect to time, which is this red symbol here in the numerator. If we divide that by 8, that should be equal to, for example, coming over here, change in water concentration with respect to time, highlighted here in red, divided by 10. Likewise, we can divide rate of change of the oxygen concentration by 9, and we will obtain the rate. In this case, we must multiply by a negative number because naturally the amount of oxygen is decreasing at any point in time, so this red quantity is negative. Rate of change of butane with respect to time will also be negative, so we can make it equal to the rate by dividing its rate of change by 2 and multiplying by, or adding a negative sign because it is a reactant. So all 4 of these will be equal to each other and equal to the rate of the reaction. Alright, now that we've seen this, let's consider this example problem. Here we have a reaction in which calcium hydroxide, aqueous solution, reacts with HCl, which is also aqueous, to make water, and aqueous calcium chloride. If calcium chloride is formed at 3 moles per liter per second, what's the value of delta HCl over delta T, or the rate of change of concentration of HCl? How quickly, what is the rate of change of concentration of HCl? Alright. Study the relations in the previous slide of this presentation. Stop and attempt this problem before continuing. Alright, here's the solution. Again, we see the reaction. the product, calcium chloride, is being formed at a rate of 3 moles per liter per second. And we are asked the value for rate of change of concentration of HCl. The rate is change in concentration of CaCl2 over time divided by 1. 3 moles over liters per second divided by 1 is 3 moles over liters times second. At this point, make a note that liters times seconds appears in the denominator of this rate expression. Concentration change per unit time. This concentration change per unit time will be the standard units for any reaction rate and for any rate of change of any substance in the reaction as well. Continuing, to find this change in concentration of HCl, we take the rate and set that equal to negative of this change divided by 2. Delta HCl over delta T then is negative 2R. And negative 2 times 3 is negative 6 moles per liter per second. It seems reasonable that if calcium chloride is being produced at a rate of 3, HCl, which has a 2 in front of it in the balance chemical reaction, is being used up at a rate of 6. Alright, now that we know what a rate is, it's time to consider rate laws. Rates typically depend on the concentration of reactants, typically exponents of these concentrations. So if you have a general reaction in which compounds big A and big B are reacting to make products big C and big T, and in which the coefficients or numbers in front of the reactants are little a and little b, the rate law is the concentration of A to some power m, concentration of B to some power n. You will see throughout this course that concentrations appear, molarity concentrations appear in brackets. Right. So we have molarities were used to powers here, and then to make these equal to the rate, they are multiplied by a rate constant K. M is called the order of the reaction with respect to A. N is the order with respect to B. And the sum of the two is the overall order of the reaction. You will see examples of rate laws and determination of rate laws in the next lecture.